Good afternoon, ladies and gentlemen. This is 4ST441, our subject statistical methods and capital markets. Today we have our third seminar and we will start. So, we'll speak about numerical summaries of time series. As said at previous seminar, in this course we prefer to work with log returns. Log returns are not bounded from below, simple net returns are, and the sum of log returns has a meaningful interpretation. We will learn how to describe the time series data by simple statistical summaries. And also we will talk about so-called unconditional, it means marginal, summaries of log returns. Maybe you learn about marginal frequencies, for example, in the case of contingency tables, yes, marginal, the side frequencies. We will also speak about some marginal summaries of these log returns. Okay, so numerical summaries. Summaries that are traditionally used in statistics will be also used for our purpose. We will use measures of central tendency. We can call this also measures of position. Yes, we will calculate some statistic, one value. If you see this value, you are able to imagine a lot of information about the position of data, yes, about the central tendency of the data set. Measures of variability, about the variability of our analyzed statistical sample, variation of the sample, yes. Measures of skewness, in some literature called asymmetry, and measures of kurtosis. On our first seminar, we started to speak about the measures of skewness and kurtosis. Maybe you remember a chart, a histogram with frequencies and with calculated measures of skewness and kurtosis. You could see only the numbers, yes, and we did not interpret these values. Yeah? So today we'll speak more about these numbers, about these calculated statistics measures, yeah? So skewness and kurtosis. Note, when computing the summaries, temporal ordering of the data points does not play any role. It's important that if we calculate some statistics, it's necessary to have sorted data set, and in the case of calculation different statistics, it's not necessary, yes? So we must know when it's necessary to have sorted in ascending or descending form, yes? Or in the case where it's not necessary. Okay, so measures of central tendencies, average log return, yes, I will speak about average for the case of log return because in the future we will analyze log returns. Average log return is calculated as simple arithmetic mean, like a summation of all log returns divided by n. N is our size, the sample size. Median can be denoted like a small letter, in our case R, because we will speak about log returns with the wave 0.5, yeah, because the median is in the middle. Median is the middle value in the sorted data set of log returns. It is very important word, sorted. Yes, for example, in ascending or descending form, it does not matter, but the sample must be sorted. Yes, because we need to find a value in the middle. When there is even number of values, it's a simple arithmetic mean of two values in the middle. It's very important to note that we have two cases. We can have odd or even statistical sample. Yes, if we have odd statistical sample, median physically exists. Yes, because median is exactly in the middle, and 1/2 of values are below the median, 1/2 of values are above median, and the median is exactly in the middle between these two halves, physically exists. And the sample is even, median does not exist and must be calculated. Yes, and there is this important sentence: when there is even number of values, it's necessary to calculate arithmetic mean, the simple arithmetic mean, between two values in the middle of this sorted sample. Yes, lower quartile and upper quartile. Yes, lower quartile denoted like 0.25 separates the data set sorted in the ascending order into 1/4 of lower values and 3/4 of higher values. Upper quartile denoted 0.75 separates the data set sorted in ascending order into 3/4 of lower values and 1/4 of higher values. Yes, so it's very easy to calculate this either manually or in software, because these statistics dividing the sample, yes, divides. These statistics divides the sample to groups, percentage groups, yes. Minimum and maximum is the minimum and maximum value, yes, founded in the sample, yes, the minimum value and maximum value. So we have here a small exercise. We will calculate several measures of central tendencies. For example, mean, median, lower quartile, upper quartile, minimum and maximum for real life time series of log returns. We will speak about the result. We will use some time series which I already sent to you, and we will try to calculate this in eView software. It's also possible to calculate it in Excel or other software, but I will show this to you in eViews. But we will calculate this a little bit later, because now we will also speak about measures of variability, which are connected with these measures of central tendencies. So exercise 8 will be solved together with another calculations. Measures of variability. Variance of log returns is calculated as summation of square differences between log returns in time t all values, yes, all values of log returns and their arithmetical mean. And this whole summation is divided by capital N, the number of all observations. This is valid for population. So not large sample, but a lot of data set. If we have only a sample, yes, some time series, shortened time series, just a sample, yes, from this large data set, there is n-1 in denominator, because this variance and this calculation must be compatible with student t distribution. Yes, later we will speak about the statistical testing and about the compatibility with the distribution, and if we analyze the population or large samples in general, yes, the distribution in large samples in general is very close to normal distribution, yes, seems to be normal. But if we have only a sample or small sample, yes, it's necessary to use the student t distribution, which is a little bit different with different quantiles, and this is the reason why we are using n-1 in the denominator, because n-1 is also the degree of freedom of this student distribution. Yeah? So for the compatibility, standard deviation of log returns is the square root of the variance, square root from variance, for example, of these log returns. Very often in most of softwares, automatical softwares, yes, when you calculate the measures of central tendency and measures of variability, you have only calculated the deviation, yes, the standard deviation. So if you need to know the variance, we must calculate a second power, yes, of this standard deviation. So another measures of variability, the range, yes. Maybe I forget to say that the variance and standard deviation is a measure of absolute variability, and also the range is a measure of absolute variability, yes. Also the interquartile range, yes, is a measure of absolute variability. So we are speaking about measures of variability and absolute measures of variability. So we can see that either range or interquartile range is calculated like a simple difference. Yes, in the first case, this R is calculated like a difference between maximum and minimum value, and for the situation of interquartile range, it's necessary to calculate the difference between two quartiles, the upper quartile and lower quartile, yes. Upper quartile are 0.75 and lower quartile are 0.25. And we will connect this exercise 9 with 8 for the real life log returns. Calculate various measures of variability, variance, standard deviation, range, interquartile range, and we will interpret the result. So also the measures of central tendency and measures of variability will be calculated in EU software. Something must be calculated on calculator, because the software will provide to you only some necessary statistics, yes, for example the deviation, yes, and we'll have to calculate variance, and the quartiles will be calculated separately, yes, and the range must be calculated manually. So we will do this in software and on calculator. Okay, we will solve example 8 and example 9. So measures of central tendency and the measures of variability. I opened here a sample with prices of company Boeing. Yes, it's downloaded from the internet. Prices of Boeing in time t. We have here 504 observations. Yes, just observation. This is not the time series like Microsoft, where we know about the frequencies. Yes, we know that Microsoft was observed in working day. This is just a time series, yes, of 504 observations. So we will work with this. Okay, so I have here a work file with this file with the prices. And first, it will be necessary to calculate the log returns, because I said to you that we are working with net returns. So we will write here in command log the command. Yeah, so we must start with series. So series space. And we will write here the name of new time series. So for example, log returns, yes, log returns, equal size, equal sign, equal sign. And now we'll write log, we'll open the parenthesis, and now it must be Boeing divided by Boeing, and in parenthesis -1, yes, -1, close the parenthesis, and one more time we will close the parenthesis. In the parenthesis you can see the ratio price in time t and price in time t -1, yes, this ratio, and log, the natural logarithm of this ratio is log return. So we can click on enter, and we have here the prices of Boeing and log returns. We will compare, we can open two charts, yes, the Boeing and log return. So please, open Boeing, open Boeing, double click on Boeing, and now view and graph, yes, view, graph, line and symbol, okay, and we can have this chart here and log returns, yes, view, graph, and okay. Perfect, yes, so we have here the prices in time t, the development of prices of Boeing, and their log returns, these prices, yes, you can see there is value 0 in the middle, and oscillation of these values around this conditional mean. And now we will calculate the measures of central tendency, which we would like to calculate, and measures of variability. So we will click on View button, and there we have descriptive statistics and tests. And we'll select this function statistics by classification. And there is a window with a lot of options. So we will select these statistics. We will select mean, median, maximum, minimum, standard deviation. We will start with calculation of first quartile. So we will write here 0.25, 0.25, because this is English-speaking software, yes? We must select here the series. So we will select log returns, and for simplification of the situation, yes, of the table which we will see in front of us, we will write here group into bins if number of values higher than, write here 1000, because we have 504 observations, yes. So this will not be valid because we have only 504 observations and we wrote here 1000, yes. And their average count is smaller than, right here, for example, 2000, yes. It's just for our purposes. Maximum number of bins, maximum number of groups, right here 1, and I think that that's all. So you can click on OK, and we can see all this table. So what's important for us? Descriptive statistics for log returns, yes. There is a table, included observations 503 after adjustments. Why only 503? I said that we have 504, but we had 504 original observations of prices. But we calculated log returns and we lost one observation. So 503 after adjustments. The first observation is NA, not available. Okay, so we have here this row all, yes, and we have here calculated the mean. If you remember the chart, yes, our values oscillated around some conditional mean, which is very, very close to 0. Median in our situation, so the value dividing the sample to two groups, yes, one group below median and one group above median, is 0. What it means, we know that 251 observations are below this median, 251 observations are above median, and one observation is in the middle, because this sample is odd. So in this situation, median physically exists, and median is directly, exactly 0, 0.000000. Okay, we have here maximum and minimum value. Maximum value you can see 0.08. Minimum value minus 0.06. There is calculated quantile, and we selected quantiles computed for P 0.25, so 25% quantile, it means the first quartile, it means the value dividing the sample to two groups. One group 25% of observation, and second group 75% of observation. Yes, one group is below this quartile, the other group is above this quartile, and its value is minus 0.01111. Yes, standard deviation. Do you remember when we talked about the variance? Variance is the second power of standard deviation. Yes, you can see that EViews cannot calculate the variance. So if you use the calculator and write here 0.02209 power function, yes, the hat powered by 2, you can see the variance, yes? The variance is only very small variance, 0.0000488, etc. Yes, you are able to calculate the second power of this standard deviation, and observation 503. So that's all from these statistics, and we will we can verify that this median is calculated correctly. So there with quantile, we will calculate this p-value 0.50. We will verify that this quantile will be equal to median if we use p-value 0.50. So please click on View, Descriptive Statistics and Test, and Stats by Classification. We must select everything the same, so mean, median, maximum, minimum, standard deviation, quantile 0.5. Then we must select log returns. Okay, we will write here 1000, there we will write 2000, maximum number of bits 1, okay, and you can verify that it's alright, yes, the median is equal to second quartile, yes, the quartile with p-value 0.50. And everything else is the same like before. Yes. Okay. So now we will calculate also the quartile, upper quartile. So please write here 0.75. Right here, yes, 1000, 2000, 1 here. And log returns. Okay. So this is the upper quartile, and it's necessary for me write this quartile to the calculator. So I will write here 0.01457, yes, and if we calculate the difference between this quartile and the lower quartile, we will calculate the interquartile range. But I don't remember the first quartile, so we will calculate again 0.25. Okay, log returns, yes, log returns. Okay, minus. So it will be quite difficult. No, it will not be quite difficult. I will write here minus button, yes. I will open parenthesis and I will write minus 0.011111. I will close the parenthesis, enter, and I will see that interquartile range is 0.025688. Yes, 0.025688. Yes. Okay, so I think that we calculated all measures which I showed to you in the presentation. And now we'll move to measures of shape, which is very often called measure of skewness. To measure the asymmetry of distribution, skewness can be used. Skewness is defined as this formula. You can see that it's really not easy. There is 1 divided by n. N is the size of our sample, the length of our time series. Summation through all t is from 1 to n, and there is the third power of differences between RT and R with stripe, so the mean from log returns, yes, in this situation. So this is only the numerator, and the denominator, there is the power 3 divided by 2, and in the squared parenthesis you can see 1 divided by n, again 1 divided by the size of our sample, summation through all t, through all observation t's from 1 to n, the size, the length of our time series, and again there is power function by 3, difference between all values of RT and the mean from log returns. Yes, so this is a statistic. Yes, skewness is a statistic denoted like gamma 1. Skewness of an asymmetric distribution is 0. Symmetric of a symmetric distribution is 0, or very, very close to 0. Rules of thumb skewness between minus 0.5 and 0.5 means that the distribution is approximately symmetric. Yes, so this is the situation where this gamma 1 is close to 0. Yeah? So only the range between minus 0.5 and plus 0.5. Between minus 1 and minus 0.5, or between 0.5 and plus 1, means a moderate skew. And smaller than minus 1, for example minus 2, minus 3, or larger than 1 means a large skew. The value of skewness can be influenced by extreme observations. Yes, this can be seen, for example, in the situation of log normal distribution. Yes, with the long tail on the top. Yes. So here illustration, measures of shape, measures of skewness. Positively skewed distributions have longer right tails. Negatively skewed distributions have longer left tails. Yes. If you remember, for example, from economics, yes, the macroeconomics and the distribution of wages, gross salaries in the population, yes, you know that the distribution of salaries in the population has log normal distribution, which is positive skew, yes, positively skewed, because the most of value, yes, is concentrated here, and there is the long tail. Yeah? So this is the situation of positive skew, this is the situation of negative skew. So there is exercise 10. Plot the histogram of log returns for the real life time series, and this is the asymmetry of their distribution by calculating the skewness. And we can try to interpret the results. We will do this also with exercise 11, where we together do this with characteristic of kurtosis. So we will continue with measures of shape, the kurtosis, as the another characteristic of shape. Kurtosis and excess kurtosis are measures of peakedness of a probability distribution, providing the comparison to the normal distribution. Kurtosis is again a statistic, yes, which can be calculated on basis of data set. Can be denoted, for example, beta 2, and the calculation can see that it's not the same, but similar, because you can see that in the previous situation we had in numerator the third power. Yes, now we have here the fourth power. 1 divided by n, 1 divided by size, the length of our time series, summation from t equal to 1 to n, so summation through all t, and there is a difference powered by 4 between all logarithms and the average logarithm, yes, the average calculated from logarithms. In denominator, you can see that the squared parenthesis is in squares, powered by 2, and inside the squared parenthesis you can find 1 divided by n, again, summation through all t, and there is a squared difference between RT, all logarithms, and the mean from logarithms. Yes, in general, yes, you can calculate this characteristic and also the previous characteristic of skewness, yes, on the basis of all data set you want, yes, because instead of logarithms you can have here, for example, in general, y in time t, the value of observation in time t, yes, so it can be generalized, yes, this formula. Excess kurtosis is defined as gamma 2. This is the reason why we used gamma 1, and now we are using gamma 2 for the case of kurtosis. Gamma 1 was skewness, yes? Gamma 2 is calculated like this, beta 2 minus 3. You will see this part of the formula in the future one more time, yes? Theoretical excess kurtosis of normal distribution is 0, yes, again. You will see later why the skewness and kurtosis is equal to 0 or very close to 0 in the case of normal distribution or symmetric distribution, yes. Okay, excess kurtosis of distributions that have heavier tails than normal distribution is greater than 0. Yes, so greater than 0 means distribution have heavier tails than normal distribution. These distributions are called leptokurtic. Excess kurtosis of distributions that have higher tails, lighter tails than a normal distribution is less than 0. Yes? So again, excess kurtosis of distributions that have lighter, yes, tail is less than 0. These distributions are called platykurtic. Excess kurtosis can be largely influenced by extreme observations, yes? So, remember these two sentences or write it, for example, on the paper or to your notebook, yes? Excess kurtosis of distribution that have heavier tails than normal distribution is greater than 0. excess kurtosis of distributions that have lighter tails, the normal distribution is less than 0. So, there is exercise 11. Using the real lifetime series of daily log returns, we'll calculate the excess kurtosis, yes, and we will speak about these results. For the illustration of characteristics of skewness and kurtosis, we'll use another data set. You know the data set about the prices of Microsoft. So I opened here the time series close price of Microsoft company. We have set here 248 observations. Yes, so we already set here the range, yes, from 2nd January of year 2020 to 14 December of year 2020. Yes, regular frequency, 5 working day week, yes, data set. So we will calculate again, like in example before, log returns. So it's necessary to write here the keyword series space. Again, for example, log returns, yes, equal sign, and now we'll write log. We'll open parenthesis, and now it will be close price divided by close price in parenthesis -1 and one more parenthesis. Yes, so we can click on enter, and again, like in the case before, in example exercise before, we can open close prices. Yes, and log returns, and we can check the chart. Yes, so this is close price. We can click on view, graph, and OK. Yes, so we can see the development of the prices and log returns. We will open log returns. Again, as you can see, not available. The first value is not available because we didn't have the price on the 1st January of year 2020. Yes, so these log returns, you can click on view, graph, we will select line and symbol. Okay, so there is the development of log returns. And for log returns, yes, we will calculate the characteristics of skewness and kurtosis, and also all the characteristics, all measures, yes, which we calculated in previous example. So we can click on view button, and we have here descriptive statistics and tests. And then we have statistics and classification, stats by classification. Okay, so we will select the mean, the median, maximum, minimum, standard deviation, skewness, kurtosis. It's not necessary to calculate quantile now. The series, we must write here log returns. So yes, we have here log returns, and again number of values, right here 1000, average count smaller than 2000, maximum number of bins 1. So we can click on OK. We will zoom this table, and we can check these statistics. In the case of previous example, I forget to calculate for you the simple range. Yes, maybe you remember the simple range is the difference between maximum and minimum. Yes, so there, in the case of this time series of log returns of the Microsoft company, there is maximum 0.11 and the minimum minus 0.0986, so it's minus 0.099. Yes. So if I write here on the calculator 0.110241 minus, and now in parentheses, yes, in parentheses, minus 0.09865, close the parentheses, enter. The range, the simple range between maximum and minimum is 0.208936. Yes, 0.208936. Okay, that's all for measures of variability, and now skewness and kurtosis. Characteristics of skewness: 0.041268, yes, and characteristic of kurtosis 6.157026. So we can return to our slide, which I showed to you before. This characteristic of skewness is 0.04, so it's very close to 0. So according to values written in my slide, this should be symmetric distribution. Yes. So later we will check the distribution, for example, in histogram, and we will see if this is true or not. Yes. And now about the kurtosis. We can see that this value, this characteristic of kurtosis is 6.157, yes, 6.157. We can decrease this value by 3, yes, we can decrease this value by 3, and we will calculate the excess kurtosis 3.157. So according to my slide, which you seen before, yes, this value 3.157, yes, is above 0, yes, and this means the interpretation is that this distribution is leptokurtic. Yes, so this is about skewness and kurtosis, and we will verify this according to histogram. This is our time series logarithm, so we can click on View button, and here we have descriptive statistics and tests, and we will select the histogram and the stats. Wow! You can see that there is a distribution, yes. We can observe here some small amount, yes, very small amount of outlying values, but really, yes, really, this shape, yes, seems to be symmetric, yes. This is a distribution. We can compare this distribution with the density, yes. So please wait a second. Just a recapitulation. There is a characteristic of skewness, characteristic of kurtosis. Yes, skewness is around 0, so it's not skewed. Yes, either to the right or to the left. Yes, it's very close to 0. So there is probably no skewness, no asymmetry of this distribution. And if we compare this with the density, we can do this. We can click on View button, and we can click on graph, and there we will select here distribution, so it's a basic type, specification is distribution, and instead of histogram we will select kernel density, yes, and we can click on OK, and you will see the distribution, yes, there is value 0, and really you can see that this distribution doesn't seems to be skewed, yes, either to the right or to the left. Now we will speak about normality or non-normality of log returns. Fitting normal distribution to histogram. The probability density function of normal distribution with mean mu and variance sigma squared is given as following formula. This is the function of x. Function in this situation is the density. How to calculate this density? It's not so difficult because we have here just 1 divided by, and there is square root from 2 times p, it's a Ludolf number 3.14 and a lot of decimal positions, times sigma squared, yes, the variance. So 1 divided by square root from 2 times p, a constant, times sigma squared, the variance, yes. Exponent, and in exponent we have here in this square parenthesis minus, so it's exponent by minus. In numerator we have the second power, the squared differences between x and mu, the mean, and this is divided by 2 times variance, 2 times sigma squared. So it's not difficult. It looks difficult, but it's not difficult. Yes, you can calculate this in Excel, for example. Yes, by simple function. R with stripe. Yes, and SR squared, calculated from the sample. See previous slide, yes, can be considered as the estimates of mu and sigma squared. Yes? So in this situation, this is the mean from log returns, yes? The mean from log returns, and the variance of log returns. Yes? So the statistics can be considered as the estimates of mu and sigma squared in this formula. And we will continue. I said about normality and non-normality of log returns. So we'll speak about exact testing of normality of the normal distribution. The Jarque-Bera test of normality is a goodness of fit test. Yes, this is based on goodness of fit. And this goodness of a test of whether sample data have the skewness and kurtosis matching a normal distribution. So we have, yes, we have imagination about the normal distribution. Yes, we know how looks the shape of real normal distribution at the particular level of significance. Yes. And we are able to compare empirical data, yes, empirical distribution, empirical shape of this distribution with this theoretical shape of optimal normal distribution, optimal at the particular level of significance, yes. So we must calculate some test statistic, which is a penalization statistic. What it means, this statistic penalizes the empirical distribution, for example, because of asymmetry. Yes? So it's necessary to write here the zero and alternative hypothesis. In original paper by Jarque-Bera, the zero hypothesis is set as the data is normally distributed. Yes, there is normal distribution of the data set. So this is the zero hypothesis. Alternative one, non-age zero. Test criterion defined by Jarque-Bera, JB, is equal to, and there you can see n divided by 6. N is the sample size, yes, the length of our analyzed time series, n divided by 6. And here, in parentheses, we have here gamma 1 squared. What is it, gamma 1 squared? Gamma 1 is skewness. It's a characteristic of skewness in squares. So, if this gamma 1, if this skewness is higher, higher and higher, either with positive sign or with negative sign, yes, this value increasing, yes, because there is a second power, a penalization, plus 1 divided by 4, and there in parentheses, powered by 2, you have beta 2 minus 3. Beta 2 minus 3 in our situation is kurtosis minus 3. It means excess kurtosis. So again, if this excess kurtosis is higher and higher and higher, also with positive or negative sign, yes, that is the second power, and the penalization is greater and greater and greater. So this Jarque-Bera JB test statistic has chi-square distribution, because chi-square distribution is used in the case of goodness of fit tests. Yes, chi-square distribution, A0 is rejected at 5% significance level when Jarque-Bera test statistic is higher or equal to chi-squared quantile 0.95 with 2 degrees of freedom. Yes, 2 degrees of freedom. So, exercise 12. Plot a histogram rescaled to a density estimate for the data set of log returns. Plot the sample quantiles against quantiles of standard normal distribution, QQ plot, quantile plot. Examine a line passing through the lower and upper quartile and the real data of log returns. That's the normality of log returns by Jarque-Bera test. Do you remember when we talked about this distribution? There is a density, yes, the density of log returns of Microsoft prices. And if you remember in our presentation, we talked about some normality testing, yes, testing of normality of the distribution, and we talked about two possible options. One option is quantile chart of quantile graph, where we will see the values and the line, yes, in one chart, and we are comparing these values with this line. And second option is to use the exact test, yes, exact test for normality testing, which is based on goodness of fit. Yes, goodness of fit. So we'll start with quantile chart. But one question at the beginning. If you see this distribution, it looks like a little bit maybe a Gaussian curve. Yes, a Gaussian curve, but we calculated some characteristics of skewness and kurtosis. Characteristic of skewness is that this distribution is symmetric. Normal distribution is symmetric. Yes, and characteristic of kurtosis was 6.157. Characteristic of excess kurtosis was -3, lower by 3, so 3.157. So we will see, we will check this with quantile chart, quantile graph, and we will talk about this. So please click on the view button. We can select the graph. And we have here the basic type, yes. In specification, we will select quantile, yes. There you can see quantile graph, theoretical values, yes. We will use these theoretical values because, okay, we can compare our values, yes, our values, quantiles of log returns, with some theoretical values, which will be here if the distribution is normal, yes. Our values are the blue values, blue points, yes, and theoretical values is the red line, yes, and if the values, our blue values, are placed on this red line, we can expect at least at 5% significance level that the distribution is normal. Mainly it's important to have these points placed on the line at the ends, yes, at the ends. You can see that it's not true in this situation, yes. There we have here a deviation, yes, and a deviation from this red line. So, according to this chart, yes, you can expect that the distribution is not normal, yes, it's not normally distributed. But now we will use exact test, exact Jarque-Bera test, about which we talked during our seminar. And this Jarque-Bera test, which is based on chi-square goodness of fit, is programmed here in eViews. So we can click on the view button, and we can again select the descriptive statistics and tests, and we can select this histogram and stats. Yes, maybe you could see here that there is calculated Jarque-Bera statistic. Jarque-Bera statistic is a penalization statistic which is calculated on the basis of sample size, on the basis of calculated characteristic of skewness, and on the basis of characteristic of kurtosis. Yes, and this Jarque-Bera statistic, this penalization statistic, yes, if this statistic is higher and higher and higher, you are more and more far away from the normal distribution. If you remember the quantile, yes, the quantile, the critical quantile of chi-square distribution, 95% quantile of chi-square distribution for 2 degrees of freedom, 2 degrees, because we have two important statistics for this test statistic, the skewness and kurtosis. This value is 5.99 or 6 point something very small. Yes, it's based according to alpha level and of course the degrees of freedom, which we can use in general too. So you can see the Jarque-Bera is 102. Yes, so it's quite a lot, and we have here a p-value. Do you remember the zero hypothesis, which was set by Jarque and Bera? The zero hypothesis claims data is normally distributed. Yes, data is normally distributed. Alternative hypothesis, there is no normality. Yes, so the zero hypothesis is, according to this result, rejected at all levels of significance. So this distribution is nice, but at the 5% significance level, this is not normal distribution. Let us summarize what we seen in previous examples. The unconditional distribution of daily log returns has a mean close to zero. You could see in this in the case of chart, yes, where I showed to you the chart with oscillating values around the zero conditional mean. Yes. Is approximately symmetric. Yes, approximately symmetric. You remember the distribution, yes, which I showed to you. Is leptokurtic and is not normal. Yes, in the case of the test, the Jarque-Bera test, we could see that it was normal distribution because the Jarque-Bera test statistic was higher than 100. However, a very common approach is to assume that log returns are conditional normal with the conditional variance, volatility, changing over time. Yes, so it's the conditional variance changing over time. Such a model is capable of reproducing the unconditional leptokurticity of log returns. Distribution of daily log returns versus distribution of k-period log returns. So this is the new small chapter. What is the difference in distribution of daily log returns and k-period returns? That's the question. So far we have explored the characteristics of one period daily log returns, and let's summarize the main characteristics of distribution of daily log returns and k-period log returns. Daily log returns and k-period log returns. So there we have here a short summary. So daily log returns. The unconditional distribution of daily log returns is approximately symmetric. Yes, with the mean close to zero. The mu very close to zero. If you remember the development, yes, that was the mean very close to zero. The distribution is highly leptokurtic. It means it has heavy tails. Events in the tails of the distribution of log returns correspond to relatively large price changes. Understanding these large changes is important for risk management. So this is the case of daily log returns. And now k-period log returns. Unconditional distributions of log returns calculated over longer periods tend to normal distribution. It means excess kurtosis tends to 0. Yes? In the case of Jarque-Bera test, there is very small penalization. Yes? Do you remember the second power of kurtosis? On the other hand, high frequency log returns often exhibit high leptokurticity. For example, high excess kurtosis is observable in intraday data, but tends to be smaller as the frequency of observations decreases. Example for weekly or monthly data, so it means transformed data, yes, from daily to weekly, monthly, quarterly, etc. Okay, exercise 13, convert, yes, or transform the real data time series of daily log returns to k-period log returns using the formula from previous seminar. This one, log return in time t for period k is equal to summation, yes, of log return in time t, log return in time t minus 1, t minus 2, t minus 3, until t minus k plus 1, yes, t time minus period plus 1. Choose k equal to 5, weekly period. What it means? It means 5-day working week. Yes, 5-day working week. 21 monthly period. The months. The February has 28 days. Yes. January 31 days, yes, and other months is, for example, 30 days, but this is working days, yes, 21 working days in 1 month, and 63 quarterly period, yes, in the case of quarterly data, 63 quarterly period. Assume no overlap. Calculate the respective values of excess kurtosis gamma 2, and you remember that gamma 2 excess kurtosis is beta 2 minus 3. Beta 2 minus 3 was a part of Jarque-Bera test. I sent to your school email addresses a data set. With new prices, close prices of Kofola company. We have here available daily data, yes, daily data only in working days, yes. So again, we are starting by second day of January year 2020, and this column, close price, you have. So I sent to you only these two columns, the date and close prices, yes. And everything else, what is here, is only for illustration for you. So if you want, you can do this at home. I will not send to you this document, this old document, yes? Okay, so I add here a time variable t, yes? It's a simple variable time, increasing time, observation from 1 to the end, yes? So, we have here date, time t, and close price, price in time t. It's possible, yes, to calculate one period log return, yes? We already calculated one period log return r in time t. it's calculated like logarithm of ratio price in time t divided by price in time t minus 1. Yes? And we have here the results. One observation is omitted because we don't have observation on 0 position. And period. Period k is locked by 1. Yes? So you can see that this is shifted by 1 position forward. Yes, there is a time 1, 2, 3, 4, etc. And period k, one observation is omitted, and period 1, 2, 3, 4, etc. Yes, so it's shifted by 1 position. And after we can calculate these returns, log returns, are in time t with period k, and k will be set equal to 5 because we have 5 working days. Period k will be set at 21 because we have 21 working days in 1 month, and finally period k will be equal to 63 because we have 3 months in 1 quarter. Yes, so 63 working days in 1 quarter. So we can calculate this first result. You can see that it's calculated like logarithm of ratio price, the close price in time t on the 6th position, and price of time t on the 1st position. Yes, and this result is here on the 5th position of k. Yes, and we can check the calculation of this log return with period k equal to 10. It's calculated like logarithm of close price in time t equal to 11 and time t equal to 6. Yes, so you can see that every fifth value, yes, each fifth value is calculated something. And according to our previous seminar and formulas written in previous slides, there is an alternative way how to calculate this result. The ratio, the logarithm of ratio of price t and t minus something. Yes, it's possible to calculate the same like summation of 5 values of log returns. Yes, so there was calculated the summation of log returns on 57, 58, 59, 60 and 61 observation. Yes, okay, so this is RT with period k equal to 5, and we can illustrate how can calculate RT with k with period equal to 21 working days. So it's necessary to check the date. Yes, the time t and the period. Yes, there is period equal to 21. Observation is 22, but you can see that there is the last day of January. Yes, 31st January of year 2020. 22nd observation. There is 22nd price, the close price, period k equal to 21, and calculation here is summation of these values of one period log return. Yes. Okay. So this is illustration for period 21, and for example period K63. So we'll scroll down and we will find here. You can check the date. Yes, 1 quarter. It's January, the first quarter. January, February, March. Yes, 3 months. So there is 31st of March 2020, 64th observation, but we know that we have here 3 times 21 working days. So period K is equal to 63, and the calculation is summation, yes, of these log returns. We know that first value is omitted, yes, so summation of these values until K equal to 63. I have here rewritten the calculated values, yes. The calculated values for log returns with period 5, with period 21 and with period 63. We can see the first column with period 5 that there is the second row of Microsoft Excel, and there is row 50, so observation 48. Yes. We have here 48 working weeks, yes, 5-day working weeks. If we copy the data, the calculated data from the left side here for months, we can see that we have here 12, yes, 12 working months and 4 working quarters. Yes, so there we only copied the calculated data, and we are able to calculate kurtosis. Yes, on the basis of the data set here, yes, you can see the function. This function is the same in English-speaking software. Yes, English-speaking Excel equal sign kurt, like kurtosis. Yes, we will open parentheses and we will select the values. So if you calculate these values and use this function kurt, you will see the result of kurtosis 4.756. Yes, and excess kurtosis is this value, this statistic, decreased by 3. Yes, and its result is 1.756. You remember that kurtosis, excess kurtosis around 0, yes, seems to be normal. Yes, and if this value is higher or lower than 0, this distribution is not normal. Yes, it's away from the theoretical normal distribution. And if you check this chart, yes, this is the chart of frequencies, the histogram of frequencies, R, T for the period K equal to 5. We selected the data from this data set. You can see that this is not typical normally distributed, but we can compare these results, not only the kurtosis and excess kurtosis, but also the chart, yes, the chart of frequencies, the histogram of frequencies, with monthly period. Yes. The calculated kurtosis, again, if you check the formula, yes, there is equal sign kurt, and we selected the data set from this part, yes. These data set are k equal to 21, yes. So this data set is selected here, and the value is 1.218. Yes. If we decrease this value by 3, result excess kurtosis is minus 1.781, and if I compare this value with the previous one, 1.75, and there is 1.78 minus. It doesn't matter if minus or plus, it's almost the same, yes, in this concrete situation, it's almost the same. So again, it's not zero, yes, you can see that there is another tail, yes, in comparison with the previous chart. Yes, there is the tail here, and in the case of the second chart, there is a tail here. So we can move to quarterly period, yes, quarterly period, and kurtosis calculated from the data above. So just 4 values, yes, just 4 values is equal to 2.472, and if we decrease this value by 3, result is minus 0.5, and this is more close to 0 than in previous cases. If we check the chart, we have here 1, 2, 3, 4, 5, 6 intervals, but if you remember, we calculated this statistic from 4 values only, yes. It's necessary to have more observation, more years, yes, because we need more quarters, and if we have more quarters, yes, we'll have a nice distribution, seems to be normal. So there we have only 1, 2, 3, 4 S values in this histogram, but according to this statistic, this is the most close to the normal distribution. But in general, if we have more and more data, yes, in our data set, so more than 1 year, yes, 10 years, 10 times 4 is 40 quarters, yes, the results will be better, yes, in general. We can conclude everything. The unconditional distribution of daily log returns has a mean close to 0. Is approximately symmetric, is leptokurtic, and is not normal. Yes, according to Jarque-Bera test, you could see that this was normally distributed. The unconditional distribution of k-period log returns, when the period is longer, tend to normal distribution. It means excess kurtosis tends to 0. Okay, ladies and gentlemen, this is the end of today's seminar. Next week we will learn about autocorrelation or dependence testing. So I hope that everything was clear. I wish you a nice day, and I hope that I will see you on the next seminar. So have a nice day and bye bye.